So let's begin our review of the copper iodide lab. Specifically, the lab is about attaining the empirical mass of the product between copper and iodide. So let's begin our review here, and let's understand that what I'm trying to do here is show you how to do the lab, how to grab the data, and importantly, how to calculate the empirical mass and how to predict the products in the reaction based on the empirical formula that you determine, and of course, how to do a percent yield. So again, the first objective was to get the empirical formula. I keep saying empirical mass, but I'm sorry. So let's talk about the reaction. So what we have here is we have elemental copper, and we're going to react it with iodine gas. We know iodine is a molecular compound. It's a non-metal. I keep pointing up here, but it's the top right of the periodic table, and it's going to be a gas, okay? Now, we're not going to start with a gas. We're going to start with iodine solid, and something very interesting about iodine solid, it likes to sublime, change into iodine gas. So here we have an example of what we call a molecular crystal, okay? A crystal of iodine molecules, okay, in some kind of arrangement, but these aren't ionic bonds, or these aren't metallic bonds, and these are dipole forces, okay? So these are weak attractive forces. They're so weak that they're able to, with a little bit of energy, go right into the gas phase, okay? So it's pretty interesting that we're gonna be dealing with iodine crystals, okay? But they're gonna sublime, skip the liquid state, and go into the gaseous state. We're actually gonna heat the lab and to drive it forward. We'll talk about that as well. So in any case, we have iodine gas that results from the sublimation. It's going to react with copper. Now, this is another example of a redox reaction, right? So copper, of course, is a metal. Metals are large atoms that have an ability to lose electrons. And then we have a non-metal here. Non-metals are those elements in the upper right-hand corner of the periodic table that are smaller and coulomically have tremendous attraction for electrons. And so electrons are going to be passed from the copper to the iodine when they collide, collision theory. And of course, we're going to make, copper ions that are positive, cations, and anions of iodine. And it's going to stick together and make an ionic compound or a salt. The question is, what is going to be that chemical formula? Now, for salts, they're always the lowest ratio, but we'll call it an empirical formula nonetheless. Any case, so the question is, what is going to be that formula? It's going to be copper with some ratio, that's a question mark, and iodine of some ratio, okay? So we don't know what it is, and we need that formula in order to do any other prediction or stoichiometry chemistry, okay, or any analytical chemistry. This is all analytical. We're determining this chemical formula, okay? And so that's the purpose of the lab. And of course, once we have this chemical formula of the salt, we can backtrack and figure out the ratio of the other compounds in order to do some stoichiometry or some more analytical chemistry that we can predict the products, all right? So in any case, let's talk about what we have to do in order to get this empirical formula, all right? We should always think about in a many-step process, not what you do first, what you do last, okay? And so we're trying to find the lowest ratio of particles, not a ratio by mass. This is a ratio of particles, mole ratios. We use the word mole to have a how many number. So how many coppers compared to iodine are in this ionic crystal? All right, we've talked about crystals before, but there is another, crystal, but we don't know its formula. Now we can cheat a little bit and know something that copper, we know copper can be +1 or copper +2. So copper iodide could be copper 1 iodide or copper 2. We know that now, but we didn't know that back in the late 1800s when we were doing these types of reactions to figure out chemical formulas. And we don't have this if we're trying to figure out what the product is of a certain reaction. So we're going to think in terms of, how do I find these ratios? So what do you do last? When you do this type of chemistry, we know that we're going to, remember, divide by the lowest ratio of moles. Once you have total number, moles is a how many number. Once we have moles of copper and iodine, we divide by the smallest number to get that ratio. And that ratio of how many gives us the ratio of the individual ions in the crystal, the lowest ratio. So always thinking what we do last, we need to divide by the moles. Hey, we need moles. To get moles, we need grams. And there is your key. We need the mass of the copper that's reacted. And we need the mass of the iodine, atoms that are reacted. Don't confuse that with I2. It exists as an I2 particle. Okay, so that is what we're after from the experiment. We need the mass of copper reacted and the mass of iodine reacted. Now, with those masses, we can of course convert to moles and of course divide by the smallest value to get the ratios. Okay, and those ratios are the chemical formulas. So we have to, from the experiment, get these values. So what is the experiment? Well, the experiment is we're going to take some copper, okay, and we're going to have a piece of copper thin foil, okay, in a rectangle. It doesn't matter the size, but it's going to fit inside an Erlenmeyer flask, okay, a conical flask for some people they call it. And there's my flask. And what I'm going to do is going to add some crystals of iodine in the bottom. Okay, now in order to get to this result, we really need 3 measurements. Okay, so before I start the experiment, start exposing my elemental copper to the iodine, what I'm going to need is I'm going to need the mass of my initial copper. Mass of copper initial. It's before I react anything with it. What's the initial mass? Now we've done these empirical formula type labs already where we had hydrates, salt with water, and we drove off the water, and the missing mass, okay, was that water. And we do that also with compounds that have oxygen. We can drive off the oxygen. But here it's a little bit different because here is an addition. We're going to add mass to the system when it reacts. So it's a nice way to think differently in terms of getting the lowest ratios. Okay, so we need an initial mass of our copper, okay? And so we scale it out, and you can watch that from the virtual lab, or we did it in class, and we have that value, whatever it might be. Then we're going to expose the copper to the iodine crystals, and then we're going to stopper it. We stopper it because essentially we don't want the iodine gas, of course, to leave. We want to build up and reach equilibrium. So the iodine, which is a beautiful purple gas, is going to do that. Okay, now it's going to react. Now, and as it reacts, the luster or the sheen or the shine of the copper is going to disappear. If you watch the virtual labs, you'll see over time, and I do it in a time lapse, you'll see the shine disappear because the ionic compound is going to coat the surface. In fact, specifically, let's think about this because thinking about it on a micro level helps us understand the macro change here. So I'm going to draw some atoms here, and I'm drawing them in a very simple cubic structure. It's probably a face-centered copper, and we've studied this, right? We've looked at the metallic crystal of copper, all right? And so let's just do this as a piece of copper being exposed. We'll talk about this being the outside. Okay, now what's going to happen, obviously, is we're going to add iodine molecule. It's not an ionic compound, it's a molecule, all right? And so this is the iodine. And what's going to happen is the iodine is going to pull electrons from the copper. The question is there a way for us to really understand and know if in fact iodine is strong enough to pull electrons from the copper? We know copper metal is a pretty non-reactive metal. That's why they use it in metal pipes or flashing in your roof. They know it's not going to rust, and they don't want your pipes under pressure in your basement or in your house to burst when they corrode into a salt and get weaker. So we know copper is pretty resistive, okay, to oxidation or the loss of electrons. Remember, the iodine is going to get reduced as it gains electrons, but it's called an oxidizing agent. Is it a strong enough oxidizing agent? It doesn't have ability to pull electrons. Well, this is something you can put in your background of your lab, but something you should check, all right? Now, I know the reaction works and it's spontaneous, but these are things we've learned previously. So if we take our standard reduction potential table back out, and I've got a big one, okay, to look at, okay, all right, and we go find our copper, okay, and we look at, okay, here's copper. Copper plus 2 loves to gain electrons, and its standard reduction potential is 0.34 volts, which is very spontaneous, which means copper doesn't like to go this way. Its standard oxidation potential is negative 0.34. So we have to have iodine, okay, gain electrons and be positive enough in terms of its voltage to overcome this poor negative. And I'll say this again, if you haven't done standard reduction potential tables, hey, it's important to understand that the iodine gains electrons so well, it is given a reduction potential of positive 0.54. When you add that to copper oxidizing, we flip the sign going this way, that's negative 0.34. So a positive 0.54 and a negative 0.34, add them together, you get overall positive volts. This tells you that iodine is a strong enough oxidizing agent, meaning anything above these metals on this side will cause a spontaneous process, okay? Notice chlorine is a little bit better, okay? Notice bromide is better than iodine, chlorine, and then fluorine. Notice the halogens, as you go up, the halogens, they get smaller and more electronegative in their ability to oxidize things. So all of these chemicals are great at causing the oxidation of these things below it. Either case, we have shown that this reaction clearly is spontaneous and would give us an overall net potential to be positive, something you have learned or may have learned. There's so many concepts here that we've touched on. Okay, so what am I showing you? Well, because of the spontaneity and the proof in the standard reduction potential tables, we know electrons are going to fly from the copper to the iodine. Okay, now, they don't really fly and meet in this gap. The iodine has to actually be in contact with it, but I'm just drawing it that way. And so what happens is the copper is going to get positive, okay, and the iodine, so the copper becomes positive 1 or positive 2, we don't know, but it's going to get positive, and we know the iodine is going to get negative 1, all right, and we're going to have ourselves a crystal lattice. Now I'm drawing +1, -1, but I don't know if that is the case. Again, I don't know until I figure out the math here and do the lowest mole ratio to see what the ratios are in the crystal. But the bottom line here is I want you to realize that the outside edge, or all the exposed atoms, I'm doing a two-dimensional model here, all the exposed ions or metal atoms, okay, is going to have iodine, okay, ions added to its outside. So it's important you realize what's happening here. I am adding excess iodine, and that's going to produce a lot of this purple gas. I know my marker is black, okay? Now, what's going to happen is this salt, which is an ionic compound right here, is going to coat the total outside of the copper. And eventually the reaction will reach completion. What's completion? Hey, the reaction stops. Why would it stop? Well, because we're running out of a reactant. Who's going to run out? Well, everyone should recognize that I'm adding the iodine in excess. I'm adding enough iodine, okay, to drive the reaction, and we'll talk about Le Chatelier's principle in a second, another application here that I'm using to get this to work in a period, okay? I'm adding iodine in excess. And so I have plenty of iodine floating around as a gas. We're going to run out of exposed copper. So we're going to call this the limiting reagent, the LR. We'll just do LR. And the limiting reagent is the reactant that runs out first. There's only so much copper on the outside of my metal rectangle that I'm going to put in the conical flask here. All right, and so eventually all the iodine will react, and eventually the reaction stops, okay, when all the exposed copper. These copper atoms I drew are on the inside, so eventually we get all of this here, and eventually the reaction stops, and there's no more that I can add, all right? And that's an important piece too as we go forward in this course. Now, let's continue on. We need, in order to get these ratios, the mass of the copper and the mass of the iodine that reacted, convert those to moles and divide by the smallest value. In order to get there, I need 3 measurements. First, we have the mass of the initial. Now, after we put the copper that we've just massed out into the flask, what we're going to do is we're going to let it either sit for 48 hours or we're going to heat. Okay, for those in the virtual lab or the ones that we're doing in one period, we're going to heat. We're going to put it on a hot plate. Now, putting on a hot plate does something. It makes the, this is an endothermic process, meaning if I put heat here, heat plus iodine solid is going to make more iodine gas, meaning if I give the iodine molecules or particles in the crystal of iodine more energy, they can overcome these attractive forces more, and therefore it's going to result in a greater amount of iodine gas. Oh my gosh, I am going to increase the concentration of iodine gas. Why am I going to do that? Because I don't want to wait 48 hours. I want to do this in 20 minutes. So here's what I do. I turn on the hot plate, around 50, not too hot, okay? But that's enough for all the iodine molecules to escape the crystal, and here's what happens. If you haven't figured it out, okay, a gas is also called a solution. It also has a molarity. This is a volume, and these particles are not dissolved, but they're floating around freely as if they're dissolved in the air. So this is a solution of gas particles, and it's a molarity. And what we know is as more of these solid crystals become purple gas, the concentration of the iodine, the molarity of the iodine gas increases. And what do we have? Le Chatelier's principle, people. Here's my stress, and here's my response. The stress is I'm increasing the iodine, the I2 gas concentration. It's not a solution, but it really is. I'm sorry, it is a solution. Gases are considered solutions, okay? And as I increase that concentration, okay, the response is for the reaction to decrease the concentration, right? Working back toward equilibrium always. And so this reaction to decrease iodine, to regain its balance, if one thinks of it, is going to shift to the what? To the right. This shift is going to the right. So by me increasing the iodine by heating and making this darker purple, and you can see it in the virtual lab, I'm essentially making the forward reaction more spontaneous. And therefore I can do this, okay, without waiting for 48 hours. And that's doing some Le Chatelier's principle. But get back to the lab, all right? After it's reached completion, and it won't take that long if we heat it, okay, what we're going to do is we're going to take this out gently, and you're going to notice you're done when you can't see any sheen or luster. The ionic compound that's created on the surface, okay, will cover all of the copper, and there will be no more sheen or shine available. And what we're going to do is we're going to gently, carefully take this copper and compound now out of the flask, and we're going to measure it. So the second step is we're going to mass out the copper and the ionic compound, which is the copper iodide. We'll just call copper and product. You need that mass. Well, why? Why do I want that mass? Okay, look carefully at my drawing. What did we really add? All the copper that lost electrons became copper plus 2 is now attracted to the iodine, copper plus 2 or copper plus 1. We don't know yet. I'm not giving that away. That wasn't a slip of the tongue or a Freudian slip. Okay, but all the copper that reacted and lost electrons is still on the copper, so it's still there. All I did is I added iodine atoms to the plus atoms. So the copper is still here. So if I take the copper in the product and don't lose any and carefully take it out with any of it flaking off, and it will flake, okay, if you're not careful, mass it out. This is going to be bigger than that. And what do I have here? Okay, what did I really add here? Yeah, I really added iodide, ions or iodine. So this is heavier because of the extra what? Iodide atoms, or ions in this case, that are now attached to the copper plus 2 that was in that crystal position. Yes, it can flake off, but if you're careful and measure it, this is a little higher. When you subtract these two values, or subtract the copper from the larger value where the iodine attached itself to, and you subtract, that's going to give you the mass of the iodine reacted, right? You just added iodide to this, okay? Yes, the copper reacted, but it's still there. So the same copper is still there, okay? And you added the iodine. Okay, next step is that now I need, okay, great, I have the mass of the iodine reacted, which will give me what? Eventually moles and mole ratio. I need the mass of the copper reacted. How do I know if the copper is still there? Well, this is an ionic compound. It's no longer in the same crystal formation. It's on the metal, but it's not part of the crystalline structure anymore, although I drew it that way. So what you're going to do is you're going to remove it. Now, when I remove it, as I show you in the video, the virtual lab, I either can scrape it or wash it off, but this will come off easily. So when I remove the ionic compound, which is no longer like the solid metal, this will get flake off. It's a light green ionic compound. It'll come off nice and easy. And so remove the solid, scrape it off carefully, and then wash it and dry it. And now we do with the what? Mass of the copper final. And how to be a copper reacted? Well, the copper that was here is in the compound. So there was copper here, right, when we started? Now it's missing. That's the copper reacted. So I haven't figured it out. These two, subtract out this from this value, and you're going to get the mass of the copper reacted. So, okay? So very simple, okay? 1 and 3 here will give us the mass of the copper reacted, and of course, the initial mass of the copper and the product and the copper, okay, with just the addition of iodine, will give us the mass of the copper. And then you're off and running. Convert to moles. Just be careful here. We're dealing with iodine atoms, not I2. Do not write a formula mass for I2. We're always comparing the atoms individually. Okay, get your moles, A, divide by the smallest number, and you've got your empirical formula. Okay, so let's take some of this off now, and let's talk about what you do for the second part of the calculations, which I did not get in class 2. Okay, so let's pretend, all right, let's pretend that I have a chemical formula here. Okay, let's get rid of all of this that's in the way. Okay, so let's pretend I do find a mole ratio from these grams to be the following. What if I have copper, okay, iodine, and what if I have, I found it to be that there is a 1-to-1 relationship. Let's say 2-to-1. I'll just make this up. 2-to-1, all right? So let's make this 2-to-1. And so let's say I find it to be this, copper I2. And remember, the mole ratios you get round off to the whole number. They should be close if we do a good job in the lab or virtual lab, okay? We should be close. So round off to the nearest whole number, okay? And the reason why it didn't come out to be a whole number is because of some experimental error. If we did this 1,000 times and locked this in to find the errors, we would come and get very close to whole number ratios like our experimenters in the late 1800s. Okay, so let's pretend it's copper I2. We got a balance now. So let's say I figured out from the mole ratios that that's the empirical formula. Okay, that's my objective number 1. My second one now is to use that formula. Let's predict and figure out a percent yield. Here's how I do it. From this chemical formula, and knowing this is the exact formulas of what? Of the compounds that I started with, or in this case, the elements that I started with, balance. All right, well, this is easy. 2 I's, 1 copper, I'm balanced, right? 2 iodine atoms, 2 iodine atoms, 1 copper. So this is easy. Okay, I balanced, and show me that formula. Now the next step is I'm going to use this balanced formula and empirical formula to get and to predict how many grams I was supposed to get. So how many grams of product. So if you notice, I have the mass of the copper, I have the mass of the copper and the product. That's the mass of the iodine. And 1 and 3 we subtracted to get the mass of the copper. If you add these together, you're going to get the mass of the product. Okay, and that's what we call a yield. That's a yield. All right? So our yield is what we're after. Now, how close is that yield, that product, we call product yield, how close is that to what we should get if there is no error? Okay, well, this is what we do. We do some stoichiometry, mole ratios, mole concept. So here's what we do. Take the grams of the mass of the copper that reacted. I'm sorry, here. Okay, that's my limiting reagent. I can't start with the mass of the iodine, although I could because I did find exactly how much, but we'll start with the mass of copper reacted. That was our limiting reagent. That's the way to start here. So take your mass of copper, whatever it is. Okay, going to convert to moles. So this will be grams of copper, right? And I'm going to get rid of grams. Grams go in the bottom. I want 1 mole. We're cool, we don't write the E. And I know that copper is generally speaking about 64 grams per mole. And now I got moles. Next step, and this might be new, we've done this in one other problem. I have a how many number of copper. I've converted this to moles. Now what's the ratio of copper to the product? What's the coefficients in front? There's nothing written there in my case, so it's a 1 to 1. So every one of these coppers makes one of these particles or formulas, right? So for every 1 copper, I have 1 copper iodide, if that's the formula you're using. Now, I know it's silly because it's a 1 to 1, but we do it just to keep what? Just to keep ourselves organized. Now, what do I have here? Okay, I now have moles of what? Moles of my product. Well, we want grams. I want to compare the grams of the product that I should get, assuming no error. Okay, easy for me to say. So the next piece here is I get rid of my mole, 1 mole, and I get my grams. I find the formula mass of copper iodide from the periodic table, right? And then I solve for grams of copper iodide. This is how much I should get. And this is a classic stoichiometric formula. I convert to a how many number. I use the ratio 1 to 1. If I know the how many copper atoms, I should know how many of these, because for every one of these, there's one of these in this chemical formula that I'm using. It may not be the same for you, depending upon what you got experimentally. Okay, this might be a 1 to 2, but I'm getting rid of copper to get something else. I'm converting my how many number here to this how many by using the ratios in front. It's a 1 particle to 1 particle to 1 particle ratio. Then using the mole concept to convert to the actual grams. And this would be my theoretical yield. And what is percent yield? Percent yield is very simple. Okay, percent yield is take your experimental yield, which we're going to add these together. So we take our experimental product. We're going to divide, not going to minus here, we're going to divide by the grams that we get theoretically here, your theoretical amount that we get from pencil and paper, and then we're going to times by 100. Now, if your experimental is very close to your theoretical, you're going to get something close to 100% yield. Okay, and what does that mean? You got low errors. You can have a greater than 100% yield, which is weird. How can you get more than that's actually possible? Well, you got some error, okay? You could be under, which is more classical case, all right? And this percent yield should speak to you in terms of your actual ratio. When you report in your lab your ratio, maybe you get a 1 to 1.7, okay? And you called it a 1 to 2 because you rounded off. I want you to actually show me that real ratio somewhere in your lab. Hey, I have 1.7. I'm under for the iodine. And maybe try to relate that to your percent yield, okay? Why am I below or over? So if you notice, if I've got a 1 to 1.7, that's kind of speaking to the fact that I have less iodine than I'm supposed to have if it's a 1 to 2. Or I have more copper, okay? And for reasons I want you to try to explain, how does that relate to your percent yield? Your percent yield can be above 100 or below 100, and I'll leave that for your thinking there, okay? For instance, some people might get a 1.07 to a 1 ratio. So that's going to round to 1 to 1, but you got a little more copper than you're supposed to, okay? A little more copper than you're supposed to, okay? How would that relate to a percent yield? All right, so in any case, you're not subtracting, you're not doing a percent error, and you should know that a percent error is how close one number is to another number, okay? This is just showing us a percentage of how these compare to each other in terms of what we're supposed to get. So percent errors are great when you have 0% error. Remember, you subtract there. Here, how close we are to a value. We love percent yield, especially in chemistry, talking about how much we're supposed to make. Okay, the star of the show, okay, in terms of getting that percent yield, okay, is this problem here that we did for a lab quiz, or a quiz that we did previously. So I hope that gives you some perspective of this great lab with so many different concepts in here. Hope that helped.